So we've always looked at numbers from the perspective of real numbers and kind of thought of every number as being part of this one system. And it turns out that another system was created along the way that incorporates some of these same properties but adds on to them. So you have this system of real numbers, and you have your rational and irrational, and then within the rational numbers you have things like integers, whole numbers, natural numbers. But really our real number system is part of a bigger system called the complex numbers, which can contain real parts but can also contain this other type of number called an imaginary number. The name is weird because people just want to not include it because it says imaginary. And also, it seems like you've kind of been tricked that you thought these were all the numbers. But the imaginary numbers are only used in some very specific instances, some electrical engineering and stuff like that. And really the case here was the idea that you hit this place where you can't finish a calculation because you only have real numbers, but you know that beyond that, it turns back into maybe part of this system. And so this was created in order to serve that purpose. And so the imaginary unit is part of the complex number system, and it says whose square is -1. So this is how they define it. It's where I squared would equal -1. And that means that the square root of a negative, we normally stop there and say we have no way of expressing that in our number system. You can now express it with this different number system called I. Okay. So if I is the square root of -1, then every time you see the square root of -1, how we would write that is by I. And so think about I squared. I squared would be like the square root of -1 times the square root of -1. When you guys think about this, every time we multiply something times itself, we get the number outside of that radical. And really, this was the unit that defined the whole system. We don't have anything in the real numbers that when you square it is negative. That's what this system is based on. So I squared is the basis of this system and is -1. I cubed, we could think of as being like I squared times I, which is really like -1 times I. And so the simplest way to express that would be as -I. And then finally, I to the fourth is like I squared times I squared, which is like -1 times -1, which is +1. And this pattern continues. If you do I to the fifth, now that I know that I to the fourth is valued at 1, I'd want to use that as much as possible. So every time I see I to the fourth, that just becomes 1. 1 times anything just becomes that other amount that we were multiplying times 1. So we can use that idea here. Really, our goal is going to be how many I to the fourths do we have? So when you see other powers of I, there's some ridiculous ones here like 231 and 120. You're really asking yourself, how many I to the fourths are here? And then is there anything else besides that that's a power of I? So I would take 231 and divide it by 4 to see how many 4s go into there. I would then get, let me see, I would get 57 with a remainder of 3. So that's telling me there are 57 powers of 4 and then 3 left over. But remember, I to the fourth is 1, and even 1 to the 57th power will remain 1. Then I have this I to the third, but I know that I to the third's equivalent, and how the simplest way to write it is -I. And this all just comes down to -I. So there's really no reason for us to ever write I with higher powers on it because it should simplify to one of these more simple forms. So same thing with 120. I want to ask myself how many I to the fourths are in there, and then are there any extra powers of I? So I would take 120, divide it up by fourths, and see how many I to the fourths I would need for that. I get exactly 30 with no remainder. So no remainder would be no I's left over, which is just worth 1. And then we're using 30 powers of I to the fourth. But again, I to the fourth is worth 1, and 1 to any power is still 1. So that's generally how the powers work. So how do we express things with this imaginary unit? You're going to work with radicals the same way you always did. And remember that we often look for the perfect squares by breaking this apart. With the imaginary unit, just to help you wrap your mind around it, I would just imagine that the first way that I branch this apart is the negative and the non-negative portion. Then from here, like usual, I can ask myself, square root of 24, there's a perfect square of 4 in there, times 6, and then look at what you know the square root of here. I now know that negative 1 inside a radical can be expressed as I. Square root of 4 can be expressed as 2. There is no other way for me to simplify square root of 6. So I have a 2 times an I times a rad 6. And conventionally, the way that we write this is we write the I after the whole numbers, but in front of the radical, so it doesn't get confused if it's under the radical or anything like that. So if we were solving an equation, for example, A here, part A has all the x's contained in this squared. So I'm going to focus on getting the x squared alone. So I do this, I divide by 3. I have x squared equals negative 4, and then I'm going to square root. So I can see there aren't any real solutions, but what about complex solutions? So negative 4 is like the square root of negative 1 times the square root of 4. This can be replaced with I and this with 2. So my solutions here are plus or minus, just like we would use before, but 2I. And I can't express them as real numbers, but I can in this complex number system. And then if we have something a little more complicated where not all the x's are contained in the x squared, and we go to imply or use maybe our quadratic formula, negative b plus or minus the square root, and I have b squared minus 4 times a times c all over 2 times a. As I simplify this, we would usually stop when we see that this radical is going to have 16 minus 20, but here I'm not going to. I'm going to let that be negative 4. And that negative 4, like we saw in the previous problem, is going to simplify to be 2I. And I can actually simplify this how I did previously. This denominator is part of both of these. So 4 divided by 2 is 2. 2 divided by 2 is 1. So you'd probably more likely see this written like this without the 1 in front of the I. So there's 2 solutions there, but they're complex. They're not real. They do have a real part and an imaginary part. All right, so how do operations work? They are still part of our number system, so we tend to still add and subtract and multiply the same ways, and real parts cannot be combined with imaginary parts, but like terms, like 2 real parts or 2 imaginary parts, can be combined together. So when you see something like an addition problem, real parts can be combined together, and imaginary parts can be combined together. And this is my new complex number. When I see a subtraction sign, I want to be a little bit careful that I understand that that subtraction is part of the terms that follow those parentheses, inside those parentheses, and distribute it. And then I would go about the same way. My real parts combined with my imaginary parts to form this new complex number. And you're going to see the same thing work through our multiplication process. There's just some extra steps now because this complex number system has a link to our real numbers, specifically that I squared value. So just like you would multiply out a quadratic when it's been factored, we're going to multiply here. So negative 20 minus 15i plus 28i plus 21i squared. So like terms here are the negative 15i and the 28i, which combine together to make 13i. And then we have to remember that I squared is like a negative 1. So this is really a 21 multiplying by a negative 1, so it's really a negative 21. And it is a real portion that can be combined with the other real portion to give us negative 41 plus 13i. And that's the complex number we get when we multiply those other 2 complex numbers together. If we practice that one more time here, we would get 16 plus 12i minus 12i minus 9i squared. So again, the like terms here right away are the plus 12i and minus 12i, which would make 0i, which is no imaginary parts. They've canceled each other out. So then I have left 16 and the minus 9, but that 9 is really getting multiplied by negative 1 because that's what I squared is worth. So this is like 16 plus 9, which is 25. And this is the cool part and why this number system works. We could all go make up our own number system. But if it had no link to what was going on and no purpose, nobody would keep it around. This one has purpose in some more complex math problems than we're going to do here, but then is also very closely linked to the real number system. We took two numbers that were complex, multiplied them together, and got a real number. Okay? And this happened because these imaginary parts canceled each other out, and we made this perfect square. And that's only going to happen in this specific instance. See how it's a 4 minus 3i and a 4 plus 3i? Kind of like that factoring difference of squares. We call these conjugates. And when you multiply together those conjugates like that, that middle term cancels out and you're only left with the perfect square ends. And in this case, that's very useful. It's useful with radicals because radicals work well with perfect squares. It's useful here with imaginary numbers because those perfect squares convert them back to real values. So the last thing we're going to look at here is simplifying division problems. We're not actually going to do division, but generally we don't leave irrational things in a denominator. Well, we call that rationalizing the denominator, meaning we want the bottom of the fraction to be rational. Right now in these two fractions, your denominator is not even a real number. So we're going to try and change that. So in part A, because there's only an imaginary part, no real part, I could just multiply by I. I can do that in the denominator as long as I also do it in the numerator because I've really just multiplied the fraction by 1. And the reason this works out really nicely is because it creates 7i squared. That will convert to a real number as we finish the problem. In the numerator, it will distribute. So I'll have 8i plus I squared. And so I will have 8i plus negative 1 over 7 times negative 1. So this is 8i minus 1 over negative 7. We usually don't leave these negatives in the denominator, so that part of the denominator gets distributed through to the numerator. So it'd be a negative 8i and a positive 1. So this would be a simplified answer, or you may see it more often written with the real portion first. Now, we didn't really do much. It's still a fraction and it still is complex, but you don't see that imaginary portion in the denominator. In part B, we want to do the same thing. It's a little more complicated because of the two pieces here, and this is where the conjugate will come in handy. We know that we can convert a complex number with both a real and an imaginary portion into a real number if we multiply by the conjugate. And again, you can do that in the denominator of the fraction, as long as you also do that in the numerator so that you're really just multiplying by 1. So we're going to get in the numerator 15 plus 10i plus 6i plus 4i squared. And then in the denominator, we're going to get 9 plus 6i minus 6i minus 4i squared. Now remember, we're going to do here, we're going to combine like terms. So 15 plus 16i, and everywhere there's an I squared, that's really a negative 1, and it's multiplying that coefficient in front of it. And then here we'd have 9, and then again, this would be a negative 1, and negative 4 times negative 1 would be positive 4. Leaving us with 11 plus 16i over 13.